we're talking about the kinematic sequence and the relationship and how that indicates speed. So let's do a little bit of background material and a little bit of a tutorial before we get into the real numbers. And let's look at the differences between linear speed and velocity. Speed and velocity are two terms that you'll hear quite often. Linear speed is how fast you're moving in a straight line, and it's the rate of change of distance. So speed equals distance divided by time. But on the other hand, linear velocity is a combination of speed and direction. So it's how fast you're moving, but it has to have a specific direction. To become a velocity, you have to know in which direction you are moving. So if a car is traveling from A to B, it could have different velocities at different times while it's driving from A to B. So for example, at point 1, I could say I'm traveling at 83 miles per hour. That would be my speed. But if I added the term northeast, so if I said I'm traveling at 83 miles per hour northeast, then now that becomes a velocity. So speed is always just a number. It's just a magnitude, and it's always positive. Whereas velocity is a number, and it has a direction. It could be a negative, it could be a positive, and then it could be in a specific direction like northeast, southeast, etc. Average speed. Average speed is the total distance divided by the total time. So that's what average speed you were going literally for the whole trip. So sometimes you're going faster, sometimes you're going slower, but what was the average? Speed is measured in miles per hour, feet per second, meters per second, depending on what country you come from. One point to note, and I find people get confused about this quite often, is you can be going around a curve, but you can still have a linear speed value. So if you're driving around a curve in your car and you look at your speedometer and it says you're doing 50 miles an hour, and you go, wait a minute, that's got to be a rotational speed. No, it isn't. It's the velocity, it's the speed that you're going in a straight line, as if you were going in a straight line at that instant of time. So you can have, and it's kind of shown here with these little vectors that I've drawn. If I were to take the instantaneous linear speed at that point, even though I'm going in a curve, it has a linear speed, and it's the tangential speed that you see there given by that little arrow. Okay, so let's talk about angular speed and angular velocity. So angular speed is how fast you're rotating around an axis. It's the rate of change of the angle around that axis. So similar, angular speed equals angular distance divided by time, similar to what we just did for linear. So in other words, we would say 360 degrees per second would be an example. That would, if you think about it, 360 degrees is one complete revolution. So that would mean I'm revolving 1 time per second. I'm going to give some examples with respect to the golf club in just a minute. So angular velocity, like linear velocity, now has to have a direction. So it's a combination of an angular speed, but around an axis. So I would say if it was going to be a velocity, an angular velocity, I would say 360 degrees per second around the vertical axis or around the horizontal axis. So in other words, I have to define the axis that you're rotating around to make it into a velocity. So that's fun. Here's a little example. Don't glaze over on me. We're going to go through some math here, and we're going to look at an example kind of using the golf swing. So you can see in that swing there, which just happens to be Grant Waite's swing on the AMM system, I've got him going from horizontal here to horizontal there. So imagine that was a true circle, and imagine the club was swinging from horizontal through 180 degrees back to horizontal again. And we're going to do a little exercise, a little math that shows us the difference between linear speed and rotational speed. So if you all remember your math, Excuse me a minute. Need another drink. But if you remember from geometry, the circumference of a circle is equal to 2 pi r, where r is the radius of the circle, and pi is just a ratio of the circumference to the diameter. And pi, it's kind of strange because they put it as a Greek symbol, but really pi is just a number. It's a fixed number. And in fact, it's about 3. Okay? So it's really 3.14159, and it goes on forever, but it's about 3. And so if we do our little exercise now with half a circle instead of a complete circle, because he's only swinging through half a circle, we see that the circumference of that half a circle equals pi times radius. So that's 3 times the radius. So let's look at a first example and say we've got a 3-foot club, one of a shorter irons perhaps, and it's moving through half a circle just like Grant is here in this diagram, and that is 180 degrees. So the distance equals half a circle. So the club is actually moving through half a circle while the shaft swings through 180 degrees. So what's the length that the club head has to swing through? We can calculate that pretty easy, in fact, because it's pi times r. So it's 3, which is pi, times 3 feet, which is the length of the club. 3 times 3 equals 9. Remember, the angular distance was 180 degrees, and so we just calculated the linear distance being 9 feet. So if it took 1 second, and that's pretty slow, but let's say it took 1 second to swing through that 180 degrees, so that means the angular speed of the shaft, the club shaft, is 180 degrees per second, because we went through 180 degrees, the shaft did, in 1 second. Now, how far did the club head move in that 1 second? Well, it moved 9 feet. So its linear speed of the club head is 9 feet per second. Why am I giving you this? Well, I'm giving you the relationship between angular motion in degrees per second and linear motion in feet per second, and how, in fact, the length of the club affects the linear speed, but it does not affect the angular speed. So let's do another example where I've got a 4-foot club. So the angular speed of the shaft is still 180 degrees per second, because he's still only rotated through 180 degrees, but the linear speed of the club head itself is now 12 feet per second. So the club head is moving faster because the length of the shaft was increased to 4 feet. So a longer club will have the same shaft angular speed in degrees per second, but a higher club head speed in feet per second. So that's the relationship of linear and angular speeds. That's a very important factor in the golf swing. So now let's look at the kinematic sequence, which is both angular and linear speeds. In fact, you're probably used to hearing the kinematic sequence being rotational speeds. Well, I'm going to introduce you now also to the linear kinematic sequence. But let's start with the one that we're used to. Let's start with the angular kinematic sequence. The angular kinematic sequence is also known as summation of speed principle. So different parts of the body, rotations, all sum up to give you the total speed of the endpoint. And that's why it's also called proximal to distal sequencing. You may also, proximal being, I'll just explain that, proximal being the nearest part of the body or the inside part of the body, and distal being the further away parts of the body. So the core section is the proximal, and the distal would be the hands and the club. It's also been called the kinetic link, but technically it's really a kinematic sequence, not a kinetic sequence. In fact, Sasho talks about the kinetic sequence, and that's a sequence of forces. The kinematic sequence is a sequence of motions. But in the past, it's been called the kinetic link, and you may see it in the literature that way. And what it is it's the sequential accelerations and decelerations of the body parts, starting with the larger, stronger, slower proximal segments moving first, followed by the smaller, faster distal segments, each increasing speed as we go. So we start with the pelvis and we go to the thorax or the chest, then we go to the arms, and finally we go to the club. And each one accelerates and decelerates. You may have heard it, an analogy like cracking the whip. Well, I'll talk about a couple of other analogies as we go along. But let's get into it now, how it refers directly to the golf swing. Here's a graph from the kinematic sequence, the angular kinematic sequence from the AMM system. Along the x-axis, you've got time through the swing. Along the vertical axis, you've got angular velocity, and it's in degrees per second, and time is in seconds. We've also got these vertical lines. This first one is address, the second one is top, the third one is impact, and the final one is finish. This grayed in area is the downswing. So we've got the rotation speeds of the pelvis, the thorax, the lead arm, and the club in the different colors. So let me see if I can get a pointer. No, I'll stick with the laser pointer. The other ones are highlighters, and I don't want to be drawing on it. Anyway, sorry, mumbling to myself there. Apologies. So let's follow the red curve. You can see that the red curve accelerates, goes up, increases in speed, and then decelerates and is decelerating as it hits impact. You can see also the green curve does the same thing, accelerates and decelerates. The blue curve, which is the arm, accelerates and decelerates. And finally, the club, which is the brown curve, accelerates all the way into impact. Now, the interesting thing, the sequential aspect of it, is if you look at the little dots on the top of the maximum of each of the curves, you'll see that the pelvis reaches peak speed first, then decelerates. The thorax reaches peak speed second, decelerates. The lead arm reaches peak third, and then decelerates. And of course, the club is the final one to reach maximum speed. So each segment is building upon each other and transferring energy from one segment to the next segment using the muscles in between across the joint. So the muscles are actually increasing that, helping increase that speed from segment to segment. And the increase in speed is really helped along by the fact that the segments are getting smaller and easier, if you like, easier to move and easier to speed up. So you can see also, while we're at it, we've got the avatar at each one of these positions. And so you can see that the club is at, this is kind of interesting, actually. A little side note is that peak pelvis speed occurs when pelvis is around about square, lead arm is approximately parallel, and club is still pointing back towards the target. So if you see a golfer reach peak pelvis speed and the club is already down and released, then they've reached peak pelvis speed too late in the kinematic sequence. And you can see now here the thorax has reached peak speed. You can see the orientation of the body. You can see the peak speed when the arm reaches peak speed, and finally impact. These two are very much closer to one another than these two are. There's usually a bigger time differential between thorax than there is between thorax and lead arm. So now you've heard probably more about the kinematic sequence than you really wanted to know or knew before. Another analogy that we can think of is you can think of the body as the stages of a rocket ship. Stage one is the large, powerful, slower stage because it's got to lift all the other stages. And so it starts off. But then when it is run out of fuel and releases, the stage two and stage three can travel much, much faster because they're lighter in weight and they've already got the boost of the first stage. And then the same with the third stage. Third stage is going to be much more rapid because it's smaller, lighter, and travels faster because of the boost from the previous stages. Also, another analogy is the car with manual shift. If you have driven a stick shift, you know what I'm talking about, is you have to start in first gear because that's where you've got most power. If you try to start in third or fourth gear, the car will stall out because it doesn't have the power to do so. So as you gain speed, you change to second gear, third gear, and to finally fourth gear. So that's kind of a conceptual idea and some analogies of how the kinematic sequence works. Let's look at the parameters that we actually measured. And one of the things that's important here is that when you think of the kinematic sequence, 9 times out of 10 people think about, oh, what was the transition sequence? Was it pelvis, thorax, arm, club? Or what was the peaking order? Was it pelvis, thorax, arm, club? And they think that the kinematic sequence is just those sequences. There is way more information in the kinematic sequence. And you can see here in the measurements that we made from the kinematic sequence. We looked at the acceleration of the pelvis, thorax, arm, and club by getting the slope of the curve. We looked at the deceleration by looking at the slope of the curve on the downslope before impact. We also looked at the maximum rotation speeds. What was the maximum pelvis speed? What was the maximum thorax speed? What was the maximum lead arm speed? And of course, club speed. Now, one point to remember, this is angular, so these are in degrees per second. It's not club head speed in miles per hour. Then we also looked at the rotational speed gains. How much speed did they gain from the pelvis to the thorax, from the thorax to the lead arm, and finally from the lead arm to impact of the club? These are all important parameters and they kind of overlooked. So when we measured all of these, we found that the pros had higher, significantly higher at a level of 0.05, higher than the less skilled amateurs. So we proved that basically in the tour pros, there is a significant difference. So the kinematic sequence is sensitive enough to give you parameters that differentiate between lesser skilled and more skilled players. So there is more to the kinematic sequence than just transition and peaking, and it is a performance measuring metric, if you like. A couple of the other interesting factors that we're measuring actually is one we called the gain factor. And we looked at the ratio of the pelvis speed to the thorax speed, and we found a factor of between 1.4 to 1.6. We looked at the thorax to arm speed increase, and we found a factor of about 1.3 to 1.5. So I guess an average about 1.5 in this case, 1.4 in this case. And then we looked at the arm to the club, and we found a gain factor of about 2.3. So you could kind of think of this as like a smash factor for the body, if you like. There's kind of like a whip factor here from the arm to the club, and the speed gain is about 2.3 times typically. And then there's the thorax to the arm, which is kind of like the shoulder, how much the shoulder increases the speed, and then how much the abs can increase the speed. So if there's a lacking in any one of these, it's basically telling you that there's a problem with that joint. Maybe the joint is weak. Maybe they just don't know how to use their shoulder, or maybe they're using their shoulder too much and not their body. So this is a good diagnosis tool. And then we even took it a little bit further, and we distilled it down to contribution in speed, or contribution in percentage of speed by each joint. So we can see how much did the legs give us, how much did the core give us, how much did the shoulder give us, and how much did the wrist give us in terms of speed measurement. Again, some good diagnosis tools that can tell you where most of the speed is coming from. So typically in a teaching pro that may be a little bit older, that hasn't been training quite as much as when he or she was still competing, we typically find that the wrist speed is where they gain most of their speed from. But in the younger players, we see a lot more coming from the body. Give you an idea of where to look and how to diagnose the swing, and then give you a little bit more guidance in where to focus. Interesting, I talked about women and men databases right at the beginning, but here's some differences in some of these kinematic sequence measurements between men and women tour players. So let's look at the maximum rotational velocity of the pelvis, the thorax, the arm, and the club, so the body segments. We see that actually the women on average are faster than the men in the rotation speed of the pelvis, 500 versus 479. About the same in the thorax speed, 700 versus 710. But now the women start to slow down and drop away compared to the speed of the men. The men's arm speed, about 970 degrees per second. The women only 940. But here we get the biggest loss across the wrist from the arm to the club. Now we see the club speed is only 2,200. I'm sorry, for the men, it's 2,200 about, and for the women, it's about 1,900. So we get quite a drop off of speed across the wrist for the women. Let's look at, and this is borne out here more where we specifically look across the joint. So we see women faster in the legs, lose a little bit at the core, lose a little bit at the shoulder, and then lose a lot at the wrist. So these are interesting statistics and could be used to help improve performance of both the men and the women. Okay, contribution by joint. The women are contributing to their swing more than the men from the legs, about the same from the core or the abs, about the same from the shoulder in terms of percentage, but the men are contributing about 56% of their speed from the wrist, whereas the women only contribute about 50% of their speed from the wrist. So men are getting a lot more speed across the wrist from the release action than the women tend to. Okay, let's look at contribution to the club head speed from the angular kinematic sequence and some of the parameters that I've just talked about. We did some correlations with our database, and let's see what happened. Well, here we go back to looking at the different factors in the kinematic speed. We've got, let me back up for a second. We're looking at peak speeds in the angular kinematic sequence, and we're looking at the correlation of these factors or these parameters to club head speed. And we did find significant correlations. Of course, the most significant to club head speed was shaft angular velocity, shaft swing speed in degrees per second. That makes perfect sense because it's closest to the club head speed. There are a couple of factors that are in between. We've got the linear speed of the handle of the shaft. We've got the angular speed of the shaft itself. And those two total up to literally what's going to happen at the club head. So you expect to see a very high correlation. And we did, 0.84. Now, we also found, though, as we back along the chain, we've come back from the shaft. Now we're coming back to the lead arm. We find a moderate correlation of about 0.55, but it is statistically significant for sure at 0.0001, that the lead arm maximum swing speed, and it's not necessarily at impact, as you can see in the diagram here, it is correlated to club head speed. So if you're going to tell your golfer to swing their arms fast, yeah, it's going to make a difference because a faster arm is going to make, in general, a faster club shaft speed, which is going to make a faster club head speed. Now, we can even back along the body even further, and we can go to chest turn and pelvis turn. Both chest turn maximum speed and pelvis turn maximum speed still correlate to club head speed. Pelvis turn a little bit less, only 0.37, whereas chest is 0.58. But that's pretty cool because that means, again, if you're turning your chest, all things being equal, and whether you got your sequence correct and whether your technique is correct, but generally speaking, a higher pelvis turn speed and a higher chest turn speed are going to result in a higher club head speed. So if you're going to be a long drive champion, then you're going to have to be able to create some huge amount of power with your legs and pelvis and chest, and you're going to have a very high pelvis turn speed, chest turn speed, lead arm swing speed in order to make that shaft rotate fast and the club head move fast. So they are key parameters that are important. One other factor it's not directly kinematic sequence, but it is related to the kinematic sequence, is the lead wrist release velocity. That's effectively how fast the angle between the shaft and your lead forearm, how fast that angle opens on release is correlated to club head speed. Makes sense, at least to me, makes sense. If you think about it, the faster that club is releasing, the faster you're going to impart speed to the shaft itself. So this is kind of what the curve looks like in a typical wrist release curve. The velocity is 0, 0, 0 on the way down, which means the golfer is maintaining that wrist angle at a specific value. Now, there are different shapes. This is just one example, but typically the release occurs later in the downswing and it's very rapid. And that's what helps increase the speed rapidly, quite a high acceleration. And it actually peaks before impact because you can think about it again, the release of the shaft at the wrist is actually going to push back on the hands. And so it doesn't peak out directly at impact. It peaks out just a fraction before impact. But it is correlated to club head speed. Okay, that's the angular kinematic sequence. Now let's look at the linear kinematic sequence. And this is very new. We've only really talked about this a little bit in the past. And I'm going to get into this in a little bit more detail because, again, we've done several correlations between linear speeds and linear club head speed. And so here we've got some data to look at. And these avatars were taken at each one of these speed peaks. I guess I should explain the curve here, the curves. You've got time along the bottom of the graph. You've got linear speed in miles per hour. Now, remember, linear speed has to be of a point. So we have to look at a point in the body and measure its linear speed. And remember, the body is curving, but like I gave that explanation earlier, even though the body is rotating or curving around, like the shoulder is curving around and the lead hip is turning, we can still calculate a linear speed because it's the tangential speed at any instant in time. And so for the lead hip, in our TourPro database, we found that the maximum lead hip speed was 2.5 miles per hour. Maximum lead shoulder speed was 7.7 miles per hour. And the maximum mid-hand speed was 22.6 miles per hour. And finally, the club head speed was 115 miles per hour. And those are the Tour average values for our database of 103 TourPros. Now, if you look at the curve, you can see similar to what was happening in the angular speed, that the linear speed accelerates and decelerates, that the red one being the lead hip, the green one being the mid-hands, the green one being the lead shoulder. It increases and decreases at the same, and it peaks out slightly later, as we would expect in a kinematic sequence. And then the blue one is the mid-hands, and it peaks out third of the three. So there is that sequential acceleration, deceleration, just like in the angular kinematic sequence, but you can see that there is an incredible speed gain from the mid-hands to the club itself. We go from 22.6 miles an hour up to 115 miles per hour. And we get the sequential motion. You can see the body posture in each one of these peak points, if you like. And so that's a great look at the linear kinematic sequence, and it happens in a similar manner to the angular kinematic sequence, but now we're looking at points in the body. So let's have a look at how they correlated to peak speeds in the downswing, peak linear speeds in the linear kinematic sequence. We found significant correlations to club head speed in the peak mid-hands linear speed. So this point here, that was correlated to club head speed. So the higher your maximum hand speed, the higher your club head speed. We found similar correlations for the lead shoulder linear speed. So the faster your lead shoulder is moving, the faster your club head's going to move. And surprisingly, we found the same thing with the chest and the pelvis linear speed. There was even a correlation between the linear speed of your chest and your pelvis. Now, these are resultant linear speeds. So in these cases, 1, 2, 3, 4 here, we're not looking at a particular component of the speed. We're looking at the total speed, the total resultant speed. The higher the resultant speed, the higher the club head speed. But if we tease out some of the components in 2 of these, we find some interesting information as well. We found that the lead shoulder linear upward speed at maximum, so the fastest that the lead shoulder was going upwards, was correlated to club head speed as well. So that tends to suggest, if you think about it, that if your lead shoulder is moving up very rapidly, it's going to pull on the arm, which is going to pull on the end of the club, which is going to help release the club. So that kind of makes sense intuitively, but it was something that came out of the data. And then this one was an interesting one too. Remember when I talked about the chest sway tracker, and I showed you the curve of how it moves, the chest center point moves towards the address position and goes past the address position. And then before impact, it moves rapidly away. In every single case, that was 100% truth, remember? In fact, the chest linear speed away from the target is also correlated to club head speed, which means that the faster your chest is moving away in the downswing or late in the downswing, it's got to be timed correctly, but late in the downswing means the club head's going to be moving faster. I know I'm throwing some interesting stuff, and I'm probably going to get a lot of resistance and a lot of questions on all of this, but this is what the data has been telling us. And this is what the curves show us. So let's just summarize. So for a faster club head speed during the downswing, high body segment peak angular speeds, high wrist release speed, high linear speeds, lead hip, lead shoulder, mid hands. And a couple of those are very specific in the directions that they have to be moving, such as the lead shoulder moving up very rapidly. And again, just in summary, an efficient kinematic sequence of both linear and angular, and the sequence of pelvis, thorax, arm, club peaking leads to an efficient kinematic sequence and a powerful kinematic sequence for both angular and linear. And don't forget that all of these motions that I've talked about have to be timed perfectly. Just having a maximum speed in a rotational speed or a linear speed doesn't mean it's going to transfer to the club. That's what the kinematic sequence is all about. It's all about the efficient transfer of the speed from the inner, bigger segments of the body out to the smaller, faster segments of the body, being the arms, the wrists, and the shaft and club. Well, that's it. Thank you for listening. And I'm very excited about the fact that Sportsbox AI can now supply you an app that you can run on your iPhone, film a swing from a front view, and get a lot of this 3D data. Now, at the moment, you can get the trackers that I talked about at the beginning, which are like the turns and the bends and the sways and the lifts. We're working on the kinematic sequence. We're doing things one step at a time. So the kinematic sequence will be something that comes out at a later date. But at the moment, the Sportsbox system gives you the 3D avatar that you can literally compare swings side by side and look at the numbers as you play through the swing. And you get the data within about 30 seconds of taking the video of your golfer on your phone.